Okay, welcome back to my channel, everyone. I am Ansar, your helping hand, and today we're going to be talking about the normal approximation to the binomial. So there's this kind of question as to like why we need this, and before we can answer that, we kind of have to think about the binomial distribution. So back in the day, or historically, calculating probabilities for binomials used to be quite difficult, right? So whether you're calculating like a particular value or it's greater than or equal to some value, both of these calculations have this binomial coefficient. And the binomial coefficient has, a lot of factorials. There's three at least, So those binomial coefficients, they can be quite difficult because factorials aren't a explicit function. You need to in order to calculate a factorial of size n, you need to multiply n things. So if you're calculating, factorial where n is 100, you're multiplying 100 things. So it's not necessarily very easy if you don't have a lot of computing power. So when n is very large, those binomial coefficients become difficult to compute. And then on top of that, if you want to calculate a range for your binomial, right, you're going to have the sum here. So the sum basically makes it a lot more difficult because now suddenly you're calculating, multiple binomial coefficients. So basically, if you had a large n and you wanted to calculate, a range for your binomial distribution and you didn't have a computer, good luck, because you would just have to do so many calculations by hand. So basically, back in the day, and this is back in the day before we had computers, right? We couldn't really, it was quite difficult to calculate binomial distributions, the probabilities for them. So we used normal approximations. We approximated the binomial as a particular normal random variable. And that was successful and useful. But then obviously, nowadays we've got computers, we've got, calculators in our pockets, we've got Excel spreadsheets. We've got RStudio. So why do we still need to do this approximation? Why do we need an approximate value for a binomial if we can get a exact value very quickly? Well, to answer that, we need to think about, how does binomial, or what are the various things that binomial distributions can model? So remember, a binomial distribution models any particular experiment where you are counting the number of successes in independent trials. So you can define a success however you want, and you can define a trial however you want. And as long as you can define those two things, then you have a binomial distribution. So yeah, in the first example, we're counting the number of people who are going to vote for Donald Trump. In the second example, we're counting, the number of native English students in MathStats 214. And then in this last example, we're counting the number of claims in a insurance policy portfolio. And specifically, we're just looking at the policies that do claim. So policies that do claim, because there are obviously some will claim once, some will claim multiple times. We're just looking at policies that claim. So in that sense, we've defined our trial to be any particular thing, and we've defined our success to be what we're looking for, what we're interested in. And as soon as you have those two, as soon as you've met those two conditions, right, you can use a binomial distribution. So for instance, in the first example, right, where X is the number of people that will vote for Donald Trump, right, we can model X as being some binomial with NP, right, where N is the number of people who are actually going to vote in the election, right? So then, so essentially that's your number of trials, and you can count those, and you can count how many people are your successes, right? So that's you're defining success to be someone that votes for Donald Trump or votes for Republican, and you have this p-value, which is the probability that any particular individual, right, any individual on the street, that they will vote for Donald Trump or the Republican Party. So when p usually means a probability, like that's kind of how we've been taught to think about it. But when you have a finite population, right, And what I mean by finite population is you can count the number of people and it ends at a particular value. So that's 5. That's a finite population. It doesn't go on for infinity, on till infinity. So when you have a finite population, the probability of something happening for any particular value, for any particular success, right? That in a sense is the same idea as the proportion of the population that has that successful characteristic. So, yeah, that's just a quick recap on the binomial distribution. So, if we knew what the true value of p was, right? If we knew what p actually was, what the probability that any individual will vote for the Republican Party or for Donald Trump, right? We would be able to make some powerful predictions. If we knew what P was before the election, we could tell you who's going to win the election. And based on that, we could decide, okay, do I want to invest in the US stock market or do I want to invest in the European stock market, or do I want to start building my factories in China versus in America based on what their kinds of trade or tariff policies are going to be. And so you can see that if you know what P is, right? P is a very powerful parameter or a powerful piece of information, because if you know what it is, you can make powerful predictions using your binomial modeling of your particular situation. But it's very unlikely that we will actually know what P is, right? This P value in the election setting, right? That could change based on what Donald Trump says in his next press briefing. That can change based on how the US Senate decides to, move a particular piece of legislation or scrap a particular piece of legislation. So that P value isn't a fixed constant that we can somehow know and then that's it going to be, that's it, right? This P value is almost always an unknown value, right? In the English students example, we can think that, the number of people or the proportion of people that speak English, we can estimate that as being the proportion of English speakers in South Africa. But then you have to consider, well, is your math stats class a representative sample of the population, of your whole population? So essentially, P is very difficult to nail down in terms of what it actually is. So if we want to go and get information about it, we have to go out and we have to go and sample people. So we get a random sample of people, right? Let's say NS people, right? And let's say this is the Donald Trump example. And then this is basically kind of what happens is you go out and you poll people. You get a random sample of, let's say, 1,000 people all across America, and you ask them, are you going to be voting for Donald Trump in this election? And they will either say yes or no, or I don't know. And then you count the number of people that have your characteristic success. So you count the number of people that are going to be equal to that are going to vote for Donald Trump, right? So once you have that number, once you have that observation of what C is, right, you could theoretically calculate the probability of seeing your C bar, right? C bar is the number of successes, being equal to an observation value. You could calculate that, but because we know that C bar is a binomial, right? It's still a binomial even if you don't sample the entire population, because we're assuming that P is this, fixed value, or P is some value that we can use, essentially. So if we take a random sample of NS, where N is the number of people in our sample, right, that should still be a binomial distribution. But if you look at this distribution is not pivotal. So we spoke about this in the last video on the central limit theorem, but pivotal distributions, basically, a pivotal distribution, the parameters of a pivotal distribution, they don't depend on any unknown values. So in the previous video, we saw that the pivotal distribution of the sample mean looks like a standard normal, and the pivotal distribution of sampling variance looks like a chi-squared with n-1 degrees of freedom. n-1 and n-1 is a value that we know. It's not an unknown value, and 0 and 1 for the standard normal are not unknown values. We know what those values are, right? So in this sense, this distribution over here is not pivotal. So in order for us to make a calculation, right, for C bar, in order to calculate the probability of seeing C bar equal to our observation of the number of people that have our successful characteristic, we would still need to know what P was for that calculation to be accurate. And so essentially this modeling it at this number of successes as a binomial, it doesn't really work, right? It doesn't work because our distribution doesn't allow us to make useful calculations, because we need to know what P is, but we're using this model, this binomial model, to get information about P. So if we're trying to use a model that needs P in the model, then we can't really use the model to get information about P, essentially. So that's what this means, right? But if we consider a normal approximation, right, where if we think of C bar as being some normal approximation, then that could be as some normal, or if it's approximated, right? If we approximate our binomial, our C bar being binomial, if we approximate it as a normal distribution, the probability of seeing C bar equal to an observation can be approximated as saying, well, let's look at what the probability of seeing a normal random variable between or in a particular range, right? That's what this Px is, an element of a range AB. That just means that x is between B and A, essentially. That's what this probability is saying. And that's a lot easier because we know how to go and get normal normal probabilities. And you might be saying, hey, well, we still now need a mu and a sigma, but we can standardize this and get a standard normal. And then once we've got a standard normal, that distribution doesn't depend on any of our unknown values. So the punchline, right, of this entire slide is that normal approximations allow us to make easy inferences about proportions. And proportions are a very important topic when they need to be. Okay, so why can we approximate this binomial as being a normal, right? Why can we use this approximation? And in order to understand this, we need to go back to the central limit theorem, right? So remember, the central limit theorem says, let x1, x2, ... xn be IID random variables with some mean, with mean mu and variance sigma squared. So if you have that set up, right, where you've got n independent and identically distributed random variables, then the central limit theorem will hold, right? And this x's, right, these random variables can be any distribution you want them to be, right? And the central limit theorem says that as you take more and more n's, right, as n goes to infinity, then your sample average, right, your sample mean, right, xn bar, that standardized, right, will be equal to a normal, a standard normal random variable. And we showed in the previous video on CLT, that this is equivalent to saying, if I sum up all of these xn's, right, if I sum up all of these x's, these x random variables, if I sum them up, as my n gets larger and larger and larger, right, I'm not saying the limit here, because if you take a limit, then here you'll have an infinity mu times infinity sigma squared, and that doesn't really make any sense. But we can think of this kind of as being the approximation part. This is as our n value gets larger and larger and larger, our sum of our x's, right, will look like a normal distribution, where the mean of our normal distribution is just the number of n's that we're summing up multiplied by our mean, and our variance multiplied by the number of samples we're taking, right? So this, I kind of went through this, how you get this implication in the previous video, so you can go and check that out. But this is what the central limit theorem says, that if you have any of these, if you have this criteria met, then when you sum all of these x's up, that they look like a normal distribution. They will look like an approximate normal distribution. And when you take the limit, they will actually be a normal distribution, but then you've got a normal distribution with an infinity mean and infinity variance. And so therefore you have to use this version when you go to infinity. Anyway, that's the CLT. Now, let's think about the binomial, right? So if we have x as being binomial NP, right? And this is now a kind of throwback to maybe prob stats 114, 144, depending on which one you had. But if you have x as binomial, right, with NP, right, remember we're counting the number of successes in n independent trials. That's what x is modeling, right? So if the that's trials, right? That's what x is modeling, right? So we can think of x, right? If we think of our n independent trials, we can think of each of those independent trials as being a particular random variable, right? So each of those n independent trials become here our x1, our x2, and our xn, right? And then the sum, right? The sum would then be our x, because if we take, right, let's say we have x is binomial with n being equal to 10, right? And what we can then go and do is we can say, okay, cool, we're counting the number of successes in n independent trials. So we can think of our x value as being the summation of each of our independent trials, right? And if each of our individual independent trials, if that random variable is either equal to 1 or 0, 1 if it's a success and 0 if it's a failure, and then we just sum all those up, and that will still be equal to x. So that's what this is saying over here. And essentially, a random variable that is either equal to 1 or 0 with some probability is a Bernoulli trial. That's what a Bernoulli trial is. That's what a Bernoulli random variable is. So we can think of our x value, right? Our x is a binomial. We're counting the number of successes. So here, yi, right? We can think of yi, y2, y3, ... yn, right? Where we think of y's, each of our independent trials as being their own random variable. And then we can go, okay, cool, y1, right, y1 was a success, so that's a 1. y2 was a failure, so that's a 0. y3 was a success, so that's a 1. yn was a success, so that's a 1, right? And then we count up all of these ones and zeros, so we count up the random variables y1, y2, y3, all the way to yn, and that's going to be the number of successes in n independent trials. But that's a binomial. So this binomial random variable can be thought of as a sum of Bernoulli random variables, and that shouldn't be that shouldn't be news or new to you. You should have learned that in your earlier prob stats courses. But now that we have this, right? Now that we have this Bernoulli random variable, right, we can use the central limit theorem, because now we have x1, x2, x3, all the way to xn, where instead of x's we've got y's, right? So those are independent, right? We said that our trials are independent and they're identically distributed. They all have a Bernoulli random variable distribution. And now we just have to think about their mean and their variance. Well, this is also shouldn't be news, there should be recap, but the expectation or the mean of a Bernoulli random variable is p, and the variance is pq. So essentially, because we've got all of this information where our x is the sum of Bernoulli random variables, we said earlier that anytime you have a sum of n independent random variables, as your n gets larger and larger and larger, that's going to look more like a normal. It's going to be approximated by a normal better and better and better as n gets larger. So we can take this sum, right, the sum over here, and we can say, hey, as n gets bigger and bigger and bigger, this is going to look more like a normal, where our mean is going to be n, the number of trials we have or the number of samples we have, times by the mean of any of our independent trials, and our variance is going to be n times the variance, and that's just equal to this x, right? X over here is the sum of your y, your Bernoulli random variables, and your expectation of y's, where y is your Bernoulli, is just p, and the variance of y when y is a Bernoulli is just pq, and obviously q is just 1 minus p, if you don't know that. So now we have this approximation. Remember this over here, this n going to infinity, that's the approximation part, right? Because obviously we can't actually sum up infinite things, because then, there's some implications and philosophical things about that. But you can't really sum up infinitely many things. But what this is saying is that as n is getting bigger and bigger and bigger, this binomial is going to look a lot closer to some kind of normal. And when we have a normal, we know how to standardize a normal, right? Because obviously these P's and PQs, right? We've got a distribution that depends on an unknown value, so it's not a pivotal distribution, so it's not useful in statistical inference, but we can standardize it. We can subtract our mean and divide by our standard deviation, which is the square root of the variance, and we can get a standard normal. So that's essentially why we can use the normal approximation to the binomial, because of the central limit theorem and the fact that our binomial can be thought of as being a sum of n independent Bernoulli trials. So that's the why, right? Now, there's this question about, like, how big does n need to be? Oops, sorry. How big does n need to be? How big is big? Well, essentially, right, in order to find this out, we're looking for a value a, right? And n needs to be bigger than a, so we're looking for a lower bound, essentially, such that this binomial distribution that we have, right, with n being greater than a, looks approximately normal. That's kind of the question we want to ask. And the way this works is the bound for what n needs to be greater than, right, will depend on what your distribution looks like. So if your binomial distribution looks bell curvy, or if it already looks normal, then your n's probably going to be quite small. And if your binomial doesn't look normal, then your n's probably going to be a bit larger, right? So if you think about the bell curve, right, or the normal distribution, it has these two specific properties that have to do with the shape of the distribution. So the first one is, no skewness, it's a symmetric graph. And the second one is this empirical rule, which is just that 68% of the data lies within one standard deviation of the mean, 95 within 2, and 99.7 within 3. So these two properties kind of are what we think of as being the kind of prototypical bell curve. So if we want our binomial distribution to look like a bell curve, it needs to have these properties in some degree, and preferably in a large degree rather than a small degree. So both of those criteria, right, will be reflected in the value of n and p. So basically your distribution will depend on n and p, and based on some combination of the two, if you can satisfy some kind of criteria with n and p, then essentially you're saying, okay, cool, this normal approximation is okay. So there's a couple of rule of thumbs. So this one over here is I'm going to say the basic rule of thumb, which is that when you multiply n times p, that's greater than 10, right? And that p is not near 0 or 1. So it's not like 0.01 or 0.001 or 0.005. It's not close to 0, and it's not like 99.99999. If you've got a p-value that's like, close to 0.5 or 0.3 or 0.7, somewhere in that range, and you multiply it by your n value, if that's greater than 10, then that's a good approximation, and then you kind of think about your normal as being okay, and you feel comfortable using the approximation. And then this over here is another rule of thumb, and this is a much stronger criteria. So the way this particular criteria comes from, right? And this criteria over here, right, has to do with the fact that has to do with p, right? So your p value will kind of determine whether your binomial looks skew, or whether it's like very symmetrical or something like that. So that value over there, that rule of thumb, has to do with your p value, right? And then obviously your n just needs to be greater than a particular, or larger than a particular level, right? And that over there, that criteria then also brings in the central limit theorem of like, your n has to get large, right? So the first criteria has to do with, okay, p being close to 0.5, making my data symmetric, and n being large enough so that I can actually use the central limit theorem, right? This one over here, this value over here, or this criteria or rule of thumb over here, has to do with the empirical rule. So essentially the way this criteria works, I'm not going to prove it or write out anything, but I'm just going to explain it, which is basically that you're looking at whether 3 standard deviations away from your mean, right? So you're looking at your mu, and you're saying, okay, plus or minus 3 standard deviations, right? If that range, because that's obviously going to be a range, you know what your mu is going to be, you know what your mu or your mean is, that's just NP, and you know what your standard deviations is, you can calculate this particular range, right? And if that range falls within all of the values that you can get, then you've got a good approximation. So basically, this rule of thumb over here, and that's the rule of thumb that's in our textbook, or a version of it's in our textbook, and it's the same. It's equivalent statements. It's just written a different way. But this statement or this rule of thumb over here is just making sure that your empirical rule gets met, that you can actually approximate your normal. You can actually approximate your binomial using your normal, because 90 or all of your data is actually within, or not necessarily all of your data, but 97 or 99.7% of your data is actually within the realm of possibilities, what your values can actually take on. So that's you don't really need to understand or know all of those criteria, but that's just basically the rule of thumb as to when the approximation is good or bad. Okay, now I just want to show you some approximations and what they look like. So if we look at a binomial where p is 0.5 or approximately 0.5, this is when n is 10 and p is 0.5, you can see it is a symmetric distribution. We've got one massive bar, and then everything else is equal on either side of it, and we can overlay a normal distribution over it. So overlay just means do that. So we've got this normal distribution over it, and you can see that it's not entirely perfect, right? If we wanted to like approximate the binomial, right, and we used a normal distribution, right, we would be losing out on all of this area. So for instance, if we were talking about this approximation, and we were using this approximation, and we were trying to figure out the area, like greater than that, or let's say, or in a particular, I'll actually do it this way. So in a particular region, right, if you're trying to approximate that your binomial is equal to 7, right, you can use this normal approximation between this value and this value, and obviously you're losing out on this particular area over here, but you're also gaining this area over here, and those usually look quite symmetric if your data is symmetric. And as you get larger and larger n's, that kind of cancellation gets much better. So here you can see we've got 100 trials and 0.5, and our normal approximation looks quite good. It's fitting it a lot better than the 10 trials, and now we have 1,000 trials, and that looks great. You can't even really tell the difference. And then if you have 10,000 trials, if someone just told you that was a normal, you'd be like, okay, that's a normal distribution. You wouldn't even think, if I covered that binomial part up, right, you wouldn't even think that that's a binomial. You just think, okay, that's a normal distribution. So that's when your p is symmetric, right? When you've got a skew binomial, right, it's a bit difficult. It's a bit different, right? Remember, the central limit theorem holds for as n goes to infinity. So your n value does need to actually be infinity in order for it to look normal. But as n gets bigger and bigger and bigger, your binomial is going to look more like a normal, but the rate at which it goes there depends on your p-value. So if you have a skew binomial, right, so your p-value here is 0.01, so that's 1/1000. So even when we have 100 trials, that does not look like a normal distribution. If we put a normal over it, that doesn't even work very well. Like, look at all of this area over here, and that area over there look very different. Sorry. Okay. And if you've got 1,000 trials, right, still not really that, it doesn't really look like that good of an approximation. Like you still have all, like, look at the difference between this area and that area. It doesn't really work out that well. When we get to 10,000 trials, it's starting to look like a normal, right? You kind of see this bell curvy shape, but it's still incredibly skew. Like you can see this doesn't really look like a very symmetric normal distribution. And when we put the normal distribution on it, it's still not that great. And if we look at, doing a probability between, for instance, x is equal to 14, right? That's the probability that this normal is between these two values. And we're adding all of this area over here, but we're losing out on very little. So we're kind of adding a lot more. So you can see when we skew, the normal approximation, it works. You can kind of see that it works, but it's not great. And then if n is, let's just try and, okay, I don't know why this is not, okay, there we go. If n is 100,000, that looks more like a normal distribution, right? But you still have this issue of like, you kind of have uneven adding and subtracting, basically. So for skews, it's not that great. But you can see that as n gets bigger and bigger and bigger, it does actually look like a normal, maybe just not in the way that we want it to look like a normal, in the sense that it's a little bit off. But as we add more and more and more, right, we're going to get a normal. But it's just, you can see that here our n is 100,000 before it even looks like a normal, whereas in our previous one, if n was 100, right, we still had a normal. So that's kind of where the normal approximation to the binomial works, or how it works and why it works. I'm going to stop the video here, but I will have a second video about how we use the binomial how we use the normal approximation. I just don't want to make my videos too long at the moment. And that will go through exactly how you go about calculating the probabilities, and something called the continuity correction, which basically makes the normal approximation a much better approximation of the binomial than you might think it is. So yeah, that's the end of this video. Please like and subscribe and comment if you have any questions or queries. And yeah, bye.